So, hello everybody. Well, first of all, I would like to thank Romain, Tobias, and Suki for the invitation and for organizing this really nice workshop. So I'm going to continue a little bit talking about magnetization manipulation with terahertz, so continuation of what Stefano was saying. And here we're going to go all the way to switching. And we're going to use some different techniques. Let me tell you a little bit about the fastest switching that have been made up to now with magnets. And this is a non-exhaustive list. But for a long time, we've been using magnetic fields. So even already 24 years ago, in this paper, they showed that you can basically switch a magnet using 4.4 picosecond magnetic field impulses. And they did this at SLAC. And so some years later, they also used Dawson switches and used the Oersted field from the current pulse to switch a magnet also very fast. We know that we can use also spin torque. And so almost 12 years ago, it was shown that you could use 50 picoseconds pulses to switch an in-plane system with spin transfer torque. And then a few years later, for the first time, we got this, I would say, 100 picosecond level switching of an out-of-plane magnet from the group of Gambardella. And in this case, it was using spin-orbit torques. And so we also know that we can use, so there's other ways. We can also use heating, and you probably all know about this very famous all-optical switching in gallium iron cobalt. So in this case, we're heating not with current anymore. We're using light, laser pulses. But there are different mechanisms in which you can exploit the heat to switch. So for example, there's this very nice, more recent paper where basically they're heating a system and using the change in anisotropy to flip the magnetization, also in very fast timescales. So we have all these different ways of switching very fast a magnet, sometimes using femtosecond optical pulses, sometimes using electrical pulses. And now I'm going to show you a few examples where we are using terahertz. And so using terahertz, there haven't been so many successful switchings, I would say. So there's been this famous work in which Alexei was involved, where they used terahertz with this gold antennas to focus the field. And they got switching in an antiferromagnet. So they changed by, I don't know if it was 90 degrees. In a picosecond time scale, and in this case they were exploiting, they were changing the energy landscape, they were changing the anisotropy with this terahertz pulse. We, a few years back, used heating with terahertz pulses to switch gallium iron cobalt, so exactly the same thing that had been done with optical pulses, but in this case just by joule heating with a very short electrical pulse, similar to what Stefano was saying, by ultra-fast demagnetizing the system, and it would flip. And more recently, we're able to use spin-orbit torque in the picosecond regime. So I'm going to be focusing on spin-orbit torque, which is where we've been working the most lately. So switching with spin-orbit torque is pretty well understood down to the 200 picosecond level. There's been a lot of work made in this kind of systems. So in 2014, there was this seminal paper from the group of Gambardella where they showed that if you have very long pulses, basically the critical threshold for switching doesn't really change all much. And this is what they call the thermally activated regime. So basically you're putting your current, you're tilting the magnetization with the spin-orbit torque, and eventually there's going to be some thermal kick that's going to nucleate a domain, and then the domain wall is going to propagate and flip the magnetization. But eventually there's a kind of divergence of the current, critical current, here when you get close to the nanosecond. And they call this a more deterministic regime because the hypothesis here, the understanding is that you nucleate a domain and then you need a certain amount of angular momentum to push the wall from one edge to the other on the device. And so if you need a certain amount of angular momentum, you need a certain amount of charge. And so as you make the pulse shorter, you need more current. So that's why here the current diverges. So then, a few years later, they actually observed this, and so they saw that in these 500 nanometer dots, when they apply a 200 picosecond pulse, they could see a domain wall nucleating on one edge and propagating. So here is for two different current directions, and they saw the domain will nucleate here or there. This has been confirmed even in larger devices, so around 4 microns. They use also 200 picosecond pulses, and they used time-resolved mode to look at the magnetization, and by looking at different positions, they could see a domain wall crossing the device. So this is pretty much accepted that in this nanosecond regime, you have to nucleate a domain and then push it from one edge to the other. And more recently, it's been observed that there's some nucleation, some stochasticity in the nucleation. So basically, when you put your nanosecond pulse, you don't really know when the domain is going to nucleate, and then you're going to see the propagation that's very fast. So this is seen here in the onset of this switching. So what happens if we go faster than the 200 picosecond mark? So there's a lot of different things that can happen. One example, one important thing that I want you to really understand is that the way you distribute the heat in the system is going to change a lot the dynamics. And this is something that we know very well from using femtosecond lasers. So if you have an out-of-plane magnetized system and you put an external in-plane field and pump this system, what you get is, well, the demagnetization of the system, and then you get this ringing, this magnetization precession that little by little damps and comes back to equilibrium. And the reason for this is that you are changing the anisotropy very quickly. So you start with the magnetization pointing here with this angle that's given by the anisotropy and the external field. And as you pump it, the anisotropy drops, and here you get a change in this effective angle. And because of this change in effective angle, you kick this precession, okay? And so this has even been used for switching in this paper that I told you about in the beginning, where basically by playing with this changing anisotropy, you can drive a full switching. And in some cases, you can switch and switch back, and so you get this kind of bullseye patterns. And this can be very well explained by this kind of precessional motion. So when you're going to do a very short electrical pulse, you're going to also induce this kind of dynamics. So we tried to do a simple model that includes spin-orbit torque and this kind of heating dynamics. So I call this a thermal macrospin model. So basically, it's just a macrospin where we add SOTs. Then we add very simple one-temperature model heat diffusion equation where you input the heat via Joule heating, and you can have some diffusion out through the substrate. And then we add some temperature dependencies for the magnetization and the anisotropy. And so if you plug some parameters for this, and you try to see what happens between a nanosecond and a picosecond pulse, so here I'm showing you for a 300 picosecond pulse what happens, at some current densities, here 1.3 10 to the 12 amps per meter, we get a switching in around 400 picoseconds, still during the application of the pulse. And as you can see, you actually kick the magnetization first in the direction of the applied field. So the trajectory, you first go like this, and then here you cross 0, and then you have the relaxation to the other side. So what's interesting is that if you don't change any parameters, but you just make the pulse shorter, now you need to increase a little bit the current density to get to the switching. And as you'll see, the pulse here is 6 picoseconds, so it's really short. You get, during that time, you get a very fast drop here in the out-of-plane component of the magnetization, but then you get a ringing. You get a, let's say, a post-pulse dynamic here that crosses 0 and goes all the way to the other side. And so if you look from the top, you can see that initially the spin-orbit torque brings you in the direction that the spin-orbit torque is torquing. So it's actually orthogonal to what we had before. And then here the spin-orbit torque stops, the pulse is finished. So you start to swing around the effective field. You get to the equator, the anisotropy changes sign, and now you go in the opposite direction. So if I put here the arrows of the effective field in the two hemispheres, you see that when you are above, you're turning around this, but when you get to the equator, now you're turning around this. And so this is just having the same parameters, just making the pulse shorter, this heating dynamics, and the amplitude of the spin-orbit torque can give you completely different pathways. So this is for macrospin, but we know that in the nanosecond, we have domain wall nucleation and everything, so This is not the full story. But we wanted to look into this direction. So the way we look at that is that we use terahertz pulses, picosecond pulses that we generate with Austin switches. So an Austin switch is just a photoconductive switch. So it's a region that's going to be insulating naturally, and when you pump it with the laser, it becomes conductive for a very brief period of time. And so this can launch a very short electrical pulse. And then we do this on waveguides, and we taper them down to increase the electric field and the current densities. We put a little magnet, and then we can look at the dynamics with MOC. So this is how it looks like. So the advantage of using these switches is that we can get very intense currents. I'll show you in a moment how intense. We get between 4 and 10 picosecond wide pulses, so these are much wider than what Stefano was showing. But one advantage is that these are purely unipolar. And of course, naturally, we have access to sub-picosecond dynamics because it's a pump probe experiment. So we're going to put our magnets here, and we've been working a lot with platinum cobalt, where we know that there's a lot of spin-orbit torque switching. So I'll go directly to the switching results. So we're looking with a magnet-optical microscope. So here, if we start in this configuration and we input a 6 picosecond current pulse in this direction under this in-plane field, we can reverse the magnetization. And we know that if we put the current in the opposite direction, we should go to the opposite direction. And so we tried all the symmetries that one should try in spin-orbit torque, and we confirmed that this is really coherent with spin-orbit torques. So we have a spin-orbit torque switching with a 6 picosecond current pulse in a rather large device, 4 by 5 microns. So this brings an interesting question, is that if we think again about the switching mechanism we had in these 500 nanometer dots, where they could see domain wall velocity and they could see the domain wall moving, and we tried to calculate what kind of velocity we should have in our 4 micron device with a 6 picosecond pulse, we get to this kind of nonsensical domain wall velocities. So we think that this is not really what's going on. We can look at the dynamics of the switching. So first I'm going to look at the sub-threshold switching, so before we go to the other side. So we're looking here at the out-of-plane component, and remember that the pulse is about 6 picoseconds, so it's really short here, it's like a Dirac. The magnetization is pointing up. Here I'm doing the experiment with no in-plane field. And so the first thing we're going to have is the demagnetization. So the current pulse comes, and the magnetization is going to drop very quickly. And then there's going to be some cooling through the substrate that gives us this long Q. There's another thing. There's also the torque, the spin-orbit torque. So we expect the magnetization to be brought out of equilibrium, far away from the effective field, and then to precess around the effective field. But because this precession is in the plane, we cannot see it. We're only sensitive to the polar component, but it should be there. So one way we can see this is by tilting a little bit the magnetization. So we're going to add this in-plane field. So what happens now is that the initial position is not perpendicular. Now we're a little tilted. And so when we have the spin-orbit torque, we go out of equilibrium, and now the precession has some out-of-plane component. And so when we do this, we actually see this precession, and we can now change the field, here's the field. So we get a phase shift of 180 degrees. We're precessing with some delay. We can also change the current, so we fall back on the other curve, and we can change again the field. So we can get all these configurations. And we can also start down, and we get the same kind of thing. So this is very consistent with this spin-orbit torque that's happening at 6 picoseconds. And we can try to fit this with this thermal macrospin model I showed you. So again, the ingredients are the same. And basically, we tried to characterize all of the parameters we had in the system, and we only had 2 real free parameters. One, which was the interface conductance that determines how quickly you're cooling, but this is pretty easy to fit because you can see it pretty obviously here. And the other one is the amplitude here, the amplitude of these oscillations. So the fit is not perfect, but it works quite well for a macrospin model. So what happens if we go all the way to switching threshold? So we struggled quite a bit to get this data because we're heating quite a bit the samples, and when we do this at a high rep rate, and a very focused probe, it becomes very challenging. But we eventually got some results in collaboration with my colleagues at Berkeley, Jeff Boca's group. So this is switching data. So here you can see the very fast drop I was telling you about. And then you can see that there's a slower swing that brings you to the other side, which takes about 60 picoseconds. And you can start on the other side. You can see the same thing. And if you change the in-plane field to current polarities, you see that you don't switch. And the dashed lines here are the model, the macrospin model I was showing you. So this is giving us some confidence that the switching we're seeing is rather coherent. I mean, at least our model supports this, and we have a very hard time believing that we can have this 70,000 meter per second domain wall velocity. So at least we're probably not switching in the same way that people have seen down to the 200 picosecond mark. So now, how much energy do we need to switch in this regime? And so this is a very, I think, interesting and encouraging question for our community. So we try to answer this. So as I told you before, the prediction is that the current density is going to diverge. And the reason is because we're doing the hypothesis that you need to use a certain amount of angular momentum. And so the current is going to go as 1 over the pulse duration, and the energy actually also goes as 1 over the pulse duration. So this is what you would expect to eventually happen, to have this divergence. And some years ago, there were some measurements where they measured the writing energy in some like actual devices, and that were, I think 50 or 100 nanometers in size, and they had the MTJ and all. And they measured this kind of divergence here, increase in the writing energy as expected. But there's also some more recent results where they haven't seen that. So is this sample dependent, or what is going on? It was not very clear. So we were wondering what is going to happen with our pulses. So for that, we need to know exactly how much current we have in our pulses. And this was not so trivial to answer. So we worked a lot on calibrating terahertz detectors. So we fabricated these kind of devices where we can delay all the echoes, all the reflections of the pulses, so we have one clean pulse. We've put some detector arms that basically are just photo switches that can catch a bit of charge when the electric field comes by, and you have both a probe beam hitting the photo switch and the current pulse coming by. Then you pick up some charge, and by measuring this charge, you can rebuild your time trace of the electric field. So this is a known method. We didn't invent this, but we just applied it to our coplanar waveguides, and we tried to calibrate them. So we are connecting this with a high-frequency probe. And so, the basic idea is that we're going to get a current here in this arm that's proportional to the Terahertz electric field when both the probe and the electric field meet. So by using this method, we can measure a current that's proportional to the electric field that's coming by, and we're changing the delay between the probe and the generation of the pulse. So we can sample the electric field as it passes by. This is how we know that we have 4 to 10 picosecond pulses. The cool thing is that we can now put our probe here, the electrical tip, and so we can now input a known pulse from a commercial pulse generator. So we put pulses that are a few nanoseconds wide, where we have a nice plateau, and we know that we have about a volt there. And so we can measure the current here, and now we can convert this into a voltage. So we did this calibration between read current and applied voltage, and we see that it's mostly linear except when we get to pretty high voltages. And we did this via this method comparing with this, and we also used another method to calibrate it, and both calibrations gave us the same relation. And so this means that we now basically have a kind of terahertz sampling scope that can go from picoseconds all the way to, right now, nanosecond, but we could extend it to microsecond pulses. So we can see all of it with the same detector, which is in situ there. And now we know that at the highest voltages, the picosecond current pulses that we can generate can have up to 0.4 amps and around 40 kilovolts per centimeter. So now, what is the current in our spin orbit torque experiments? So this is where we wanted to get. And so these are very recent data that we're still analyzing. So we are using our commercial pulse generator to go all the way down to 200 picoseconds. Well, here it's more 500 picoseconds. So we measure the critical current density and the energy. And so now the question is this going to go up, keep going up, or what's going to happen? And so the answer is that the current goes up, but not so much. And so the energy is actually keeps decreasing, and quite a bit, by more than an order of magnitude. And we are pretty sure about the energy because we can really see how much, we can see the pulses going to the sample and coming back, so we know how much energy we're really delivering to the load. This is pretty encouraging. The energy consumption keeps going down as you make the pulses shorter. You go into the terahertz. This is very good news, I think. And so we can also look at different types of magnetic systems. So we tried all of this so far, and they all work. We can switch with around 6 picosecond pulses, platinum cobalt, which I already showed, tantalum cobalt coffee B, and also even there should be a bar here, a cobalt gadolinium bilayer with a platinum underlayer, which is a ferry magnet. And so as you can see, the current that we need for switching keeps going up, but especially for the ferry magnet, it doesn't go as high. And when you look at the energy, which you can also scale ideally if this could still work the same way in a 100 nanometer dot, goes really, really low, especially for the ferry magnet. So yeah, this is pretty new, so we're still looking into this, but the good thing is that we can switch. So far, everything that we've tried, every ferromagnet and ferry magnet works. We seem to see a higher efficiency in the ferry magnet, which is something that people have been saying for a while. If you want to know more, you can go see the poster from Eva. And before I finish, in the last minute, I just wanted to make a bit of publicity, because this year we've had a few fun results that you might be interested in. So we've been able to do ultra-fast optical switching in this ferromagnetic spin valve where we have no rare earth. So this is a kind of a spin transfer torque like device. And by just laser pumping, we can switch the free layer here to both directions. We can choose to make it parallel or anti-parallel, and this is happening in hundreds of femtosecond time scale. And the mechanisms are still not well understood. So we would be very interested if you have any thoughts on this. And we also had recently another result with some peculiar switching where we think this is more similar to the precessional switching I was showing you before that the group of Alexei showed in YIG. The only thing is that we're doing this without any applied field. And so we get, again, this kind of bull pattern switching. And of course, a bit of publicity for the students that came with me. So Eva, I already told you about that she's working on this picosecond spin orbit torque. Alberto has a poster on, so very recently we've been measuring spin accumulation optically. And so we're very excited because we're measuring tens of nanoradians in some cases, which has been a struggle, but this opens up a lot of possibilities to characterize the spin currents that we're seeing in these kind of systems. And also we have a poster from Harjinder on Terahertz emission. So thank you for your attention. And just to conclude, so I showed you we can see picosecond spin orbit torque switching in many systems. And the reversal to us seems to be coherent at this picosecond time scale. We're still running more simulations to understand this. The fast heating, we believe, is beneficial when you get to this very fast time scales. Basically, the heating when you go slowly, a lot of heating is lost and not used for switching. Here, you heat more, but you can use that to assist the switching. And switching energy, therefore, goes down with pulse duration. So I think there's a lot we can still do with this kind of, I've heard of all these high field values that people are getting. So I think when I see the values I'm using for switching, you're very, very close to getting there. So yeah, thanks again for your attention. If you have any questions.
Okay, thank you very much.